Good morning, everybody. Thank you. I've got the instructions for the quiz sheets being turned, how to turn in quiz sheets, that kind of stuff. This should be old news for those of you having last semester. For those of you that didn't, just do your best to follow the instructions. The key part, right, is name and total number of points on your quizzes. I don't need to know the number possible. I've got that information. I didn't hand out enough quiz points. I think I did this last semester in Physics 2A as well. So it'll be like out of 20, not 50 or something like that. I'll make sure you get the credit that you deserve, right? So if you have any questions about your score, just let me know. If you don't have your quiz sheets right now, that's okay. These can be turned in any time before next Friday, right? Just make sure everything gets turned in by next week. Because I don't like taking anything during finals week except for doing the test topics. All right, and this will play whenever I remember to play it at the start of classes. We've been skipping around just slightly because of the lab schedule and things like that, and so I want to do a little bit of a backpedal and get the decay processes down, these alpha, betas, and gammas, and then refer to what we did yesterday and move forward into measuring radioactivity. So the three types of radiation are alpha, beta, and gamma. There are subsets of these. We'll get into that a little bit in beta. But let's start with alpha. Now, remember, we know what the alpha particle is. It's a helium nucleus. So let's look really closely at helium over here. Helium, atomic mass 4, atomic number 2. How many protons in helium? 2. What?
You did this wrong too.
No, we don't. Get in here.
Literally.
Get in here.
Literally.
Tell me how I do this wrong.
You have to specify it's a helium with 1 nucleus. You can say a helium nucleus.
So she's right.
I am.
She's right. This is true. Physicists are lazy. Chemists are anal.
Yes. It's all
There.
It's very true.
We're friends. We're friends.
We are.
We're good friends.
Already.
And I'm still going to come by and find you after.
Yeah. But I just heard you say that and I had to say.
She corrected me earlier today too, where she was wrong.
I was right.
I was wrong with the sign on the work for thermodynamic process. Work, obviously, when the piston goes up is positive. Up is positive.
Obviously not.
You're saying that down is positive.
Yeah.
Which is fine. It's just weird.
But it works.
Okay. Helium 4, I apologize. Correction stands. All right, so for the helium 4 nucleus, right, how many protons? 2, atomic number 2, right? How many neutrons? 4 minus 2 is 2, right? Okay. So an alpha particle is a helium nucleus, right? It's standard helium. You don't need to call it helium 4, although technically accurate to do so. So there's an example here, right? There's radium, okay, 226, okay. So if that isotope of radium undergoes alpha decay. In other words, the nucleus is going to emit 2 neutrons and 2 protons together. Then there's a calculus here, right? Okay, where whatever we start with, the symbol A for mass number and the symbol Z for atomic number. It's backwards, I know, but that's just the way it is. Okay, if we're going to get a helium nucleus out with atomic number 4 mass number 4 and atomic number 2, then kind of like all chemical equations, we need to make sure to balance. There must be a conservation of mass and charge on either side of this arrow. And if we've kicked 4 out of it, that means that whatever's left over has to be minus 4 in its mass number, and minus 2 in its atomic number. But what happens, so radon 226, right? Okay, it's radium, where's radium? Okay? Radium-226, okay? If we drop the number of protons by 2, does it stay radium? What determines what an element is? The number of protons, right? And we've just gotten rid of 2 of them. So the atomic number is no longer 88, it's 86. And that's not radium, that's radon. I know it's confusing, okay? This was maybe a bad example. But it does undergo alpha decay. So radium undergoes alpha decay, becomes radon gas, because the number of protons in the nucleus has changed. This is called transmutation of the elements. This is what the alchemists were after. What were they trying to do? They wanted to make gold, right? They wanted to turn lead into gold. There's lead, number 82, right? And so now we know how to do it, right? If we take lead and we have it do alpha decay, what happens to the number of protons? Decreases by 2, right? So we go lead, 1, 2, now we're at mercury, 80, okay? Gold's right there. Uh-oh. We want to drop by 1, but if we have, but all we've got is alpha decay so far, right? So alpha would drop it by 2 to get us to PT. What's PT? Ooh, stop there. Right? Platinum better than gold? More expensive anyway, right? Okay. So 2 alpha decays would get us to platinum. We can actually change what the element is by messing with the number of protons in it. We can convince lead to do 2 alpha decays, we get to platinum. Spoiler alert, if we get platinum to do a beta decay, it goes up and we would get gold. The problem is that the amount of energy it takes to do that far exceeds the cost, like the amount of gold you get out of that is way lower than the amount of energy you had to put in to make it happen in the first place. Okay? It's been done, it's very difficult. The process is very similar to that of making nuclear bombs, okay, right? But it's just not practical, right? It can be done, it's just not practical. In nature, transmutation happens all the time because anything bigger than lead, 207, is radioactive. And so naturally things will decay and undergo different processes to get to a point of stability we'll talk about in a second. But you can see here, right, that our radium has turned into radon, right? It was 88, alpha particle went out, we dropped the atomic number by 2, we dropped the atomic mass by 4 to conserve the mass, and our alpha particle comes out the other side. You'll note that in nuclear chemistry, nuclear physics here, the symbol for the alpha particle is helium-4, right? Helium-4 2. So that's what it is. All right. So that's alpha decay. The kind of alpha decay is closer than you think. What's this a picture of? Yeah, okay, so now I know how many of you actually pay attention to your smoke alarms. Okay, because this is the inside of a smoke alarm. Okay? Most notably seen, or I suppose you could argue not seen, in the middle of the night when it starts beeping and you wake up angrily, rip it off the wall and throw it on the floor, right? You don't see the insides until the next morning. Notice the yellow sticker. What's inside of your smoke alarm? A radioactive alpha emitter. It tells us what isotope it is. I can never say this word. It's supposed to be americium, but I think it's pronounced americium, something like that. I get fouled up in all the IUs. I always sometimes say americium, but that's not right either. Right, 241. Okay, it's it's right there. Oh, does anybody know why some of these are not black and they're like outlined? These are synthetic. In other words, they've been created by humans in the lab. The things that are white, we've never seen in nature, right? We've made them, we have never seen them in nature. So this is a synthetic isotope, okay? It undergoes alpha decay, right? Does it indicate on there? It gives us it's 1 microcurie, 37,000 becquerels. It doesn't say whether it's alpha, beta, gamma, but it's an alpha emitter, okay? And it's sending out a stream of alpha particles that then hit a detector, okay? And as long as those streams of alpha particles are hitting that detector, smoke detector happy. But if smoke gets into that beam of alpha particles, what happens to an alpha particle when it hits basically anything? It just it gets absorbed. Its energy goes away. Remember, alpha can't go through your skin. Can't really go through the air very far, right? It's easy to stop an alpha particle. And so smoke particles get in there, okay? We won't say whether or not those smoke particles maybe came from the food you were cooking in your kitchen, but smoke gets in, blocks the beam of alpha particles, very sensitive. Sensor senses a drop in voltage because the charges are no longer coming, beeping ensues, right? So here's an example of a radioactive element that is keeping people alive, right? That extra warning that people get when this thing goes off in a legitimate fire is the time it takes to safely get out of the structure. So if you are disposing of your smoke detector, please do not throw it in the trash, okay? Believe every hardware store in the state of California is required to take them. It's because of that radioactive isotope in there. They want to make sure to take that out and be able to recycle it properly. Whoa, my gosh, what's going on here? Okay, problems. This is beta decay. So, what do we know about beta particles? What are they? They're electrons. They're really energetic electrons. So we better start there, okay? So a beta particle, the symbol for a beta particle is a lowercase e for electron, and then its mass is 0. Now technically the mass of an electron is not 0, okay? Electrons have mass. It's just on the scale of neutrons and protons and nuclei, it's 1,000 times less than that of a proton or a neutron, so it's just so small we don't keep track of it. So mass number is 0 in terms of conservation of mass number. And then we know electrons don't have protons in them, but we do know that electrons have negative charge, right? So charge number is -1. So that's the symbol for a beta particle. Okay, so let's concentrate on the left-hand side. Let's not worry about the right-hand side for right now. So we got carbon-14 up here, right? Okay, so we've got carbon-14, and it undergoes beta decay. We know the electron comes out, whoops, 0, -1. Okay, so to conserve mass number, right, nothing changes, right? We got 0 on the other side, so we end up with 14 still, right? But what number do we add to -1 to get 6? 7, right? Okay. So under beta decay, the atomic number increases by 1. And so what is 7? It's nitrogen. Okay. So when carbon-14 undergoes its beta decay, it turns into nitrogen-14, okay? Which is the stable version of the isotope. Does anybody see a problem with this? No? What do you mean it's a charge? Too many charges? Too many electrons? What the heck? Electron has no business coming out of a nucleus. What's in the nucleus? Protons and neutrons. Where are the electrons? Quantum, I don't know. They're somewhere else. Cats. They're not in the nucleus, right? So what gives? Where did this electron come from? It came from the nucleus. So, how is that possible? That was the question that nuclear physicists, quantum mechanics were trying to solve. They were trying to figure out what was going on. And Bohr and others were, they'd done quantum mechanics with the electrons around the nucleus. Now they were trying to figure out the nucleus. And it's like, what's going on? And then they went and experimentally they knew the electrons were coming out of these radioactive particles. But then they found something else. Another particle called a neutrino. Well, in this case, an antineutrino. Yeah, okay. So, neutrino is I think it's a Latin word for like little one. Little insignificant one, I think is how it translates. For a long time, we thought neutrinos had no mass. We were wrong. We discovered that about 15 years ago. They actually do have mass. It's just really, really, really tiny. So technically, neutrinos do not move at the speed of light, and they are not a photon. They're something else. The neutrino was required to conserve energy in this reaction, but it still doesn't tell us. I'm going to strip it off of this one over here, because it actually doesn't matter that much. It still doesn't tell us why an electron would be present in the nucleus in the first place. And so the neutrino was a discovery that was like a stepping stone that let us get to the answer of what's going on here. And the answer is neutrons can decay. What's a neutron? Bless you. A neutron, right? What's the mass of a neutron? What's it similar to? Proton, right? What's the mass of a proton? Singular proton, all by itself. Atomic mass number. 1. Right? Like it's just a proton. 1. Okay. So a neutron has a mass of 1, but a charge of 0, doesn't it? What if, maybe, just maybe, this neutron, keep doing that wrong, kicks out an electron. If a neutron got rid of a negative charge, what would it be? It would be positively charged with the mass of a proton. In other words, it would be a proton. So if the neutron, what does it mean for something to be neutral? 0 net charge. But how do you get 0 net charge? You have to have equal amounts of positive and negative. The neutron's no different. Actually, it turns out to be very different. More on quarks later. Okay? But neutrons don't turn out to be just magically 0. They are a balance of positive and negative charge. That's a neutral net charge of something that has the same mass as a proton, otherwise known as a neutron. But if that neutron could decay and discharge its negative charge in the form of an electron with a mass of 0 but just negative charge, what's left behind is the mass of a proton with positive charge, which is a proton. So this is called neutron decay, and we get the proton out on the other side. Notice the mass number is conserved. It's 1 on both sides of the arrow. The charge number is conserved. It's 0 on both sides of the order. But what we think is happening in the nucleus, in order to become stable, a neutron will eject an electron, turning itself into a proton. That means that we've not changed the overall mass of the nucleus. We've gained a proton, which transmutes it positively by 1, right? And that's why beta particles are electrons and why electrons are coming out of the nucleus. Neutrons are decaying. Now, in order to explain the neutrino and these electrons and this decay, physicists discovered the fourth of the four fundamental forces that make up our universe. This fourth force is the one that mediates this transition, kind of causes it to happen or gives us predictive power in understanding what's going on. This force is stronger than electromagnetic repulsion. It's weaker than the strong force. Anybody have a catchy name for it? Yeah, neither did physicists, and they called it the weak force. So you have the strong nuclear force and the weak nuclear force. What does the strong nuclear force do? Glues everything together, right? Keeps nuclei from flying apart, right? What does the weak nuclear force do? Governs beta decay. It governs, in more general terms, it governs radioactivity. You can think of it that way. But specifically, it governs beta decay. So, congratulations! Achievement met! You have now been taught all four of the fundamental forces of the universe. Gravity, which actually turned out to not be fundamental at all, so scratch that. Three fundamental forces of the universe, which they are electromagnetism, Coulomb's law essentially, okay? The strong nuclear force and the weak nuclear force. That's it. Everything you know and see and experience at their fundamental levels can be described by the interactions of those three forces. It's nice knowing you have a good life. But it's an amazing. There's two things that are amazing about this to me. Okay, number one, I think it's actually incredible that the universe could be this way. When physicists run around saying the universe is simple, we don't mean it's like mathematically simple. We mean we can boil down everything to these fundamental forces that govern what is going to happen. So, if the universe truly is like this, that to me is elegant, it's beautiful, it's awe-inspiring, it's amazing. I think it's equally amazing that we have, as a species, have gotten to a point where we can even think of, let alone communicate, that simplicity. Like, the language, the mathematics, the conceptual reasoning and understanding, as far as we know, aardvarks aren't doing this, right? Okay? I kind of suspect the dolphins a little bit, right? And octopi. But like, as a species, to get to a point where we can conceive of our universe in such simple terms is absolutely incredible to me. I mean, think about this. 400 years ago, we were still bleeding people to let the demons out, right? Like, we've come a long way in a short period of time. And I think we're struggling with that a lot. We've advanced so quickly. I think our scientific and moral and philosophical understandings have gotten far beyond what we're sort of capable of ingesting. My proof is social media, okay? But it is really amazing. Really amazing what we've been able to do. Anyway, back to this. Okay, so what's going on? In regular beta decay, we get an electron out. We increase the atomic number by 1. See that, right? Okay. And we get this thing called an antineutrino out. Well, antineutrino, it literally means opposite of the neutrino, okay? It turns out that there's another kind of beta decay that happens, where instead of an electron being pushed out, a neutron can eject its positive charge, okay? Leaving behind, don't think about what it leaves behind, it's just bad, okay? So what goes out is something that has the mass of an electron but a positive charge, otherwise known as a positron, which is literally an anti-electron. The word anti in particle physics refers to the fact It's the same thing with opposite charge. So an anti-electron is an electron with positive charge. What's an antiproton? It's a proton but negatively charged. Okay? So I will try to be very clear. I'm actually probably never going to ask you about this. But if we are talking about it, I will always refer to this second kind of beta decay as positron decay. Not all physicists do that. A lot of them do, but some of them rightly refer to both of these as beta decays. Beta plus, beta minus, sometimes what they call it. I refer to the electron coming out as beta decay, because a beta particle is an electron. I refer to the other one as positron decay. It's beta decay, it's just with opposite signs on it. And it's the positron decay that actually kicks out a neutrino. The beta decay kicks out the antineutrino. The point is that this stuff does get difficult when you get down into the weeds. For us, it's sufficient to know that in beta decay, which is an electron coming out of the nucleus, there's a reason. Neutrons are doing some weird stuff. And there's another kind of beta decay called positron decay. Don't need to worry about the details. It means a positive electron, an anti-electron is coming out of the nucleus instead of an electron, a normal negatively charged electron. We will cycle back to this towards the end, maybe next week sometime. Or no, this Thursday, because this Thursday is the last day of lecture, isn't it? Because what's happening next Tuesday? Review for the exam that's happening on Thursday, right? And your final exam is going to be a test autopsy, right? Not an exam. No matter how many times I say this or post it on Canvas, people still think that there's an actual test during the finals week. There isn't. It's your exam autopsy, right? You come in and correct what you did the week before. Okay, just making sure. So that is beta decay. And then there's gamma decay. Gamma is, so basically what's going on in the nucleus is almost identical to what's going on in the Bohr model of the atom with electrons changing their energy and energy levels. Turns out nuclei have energy levels inside them. There's a type of quantum mechanics you apply to the nucleus and find all the energy levels. But in gamma decay, what's going on? So here, we got boron turning into carbon. And you can identify what decay that is. I mean, even if they didn't tell you an electron was coming out, boron 12 with an atomic number of 5 becomes carbon 12 with an atomic number of 6. What kind of decay is that? That's beta decay, right? Because beta is you go up the periodic table, right? You go up an atomic number. To go down, it's alpha, and you're always going down by 2. By beta, you're going up by 1. Always 1, okay? So I know because the atomic number changed by 1 positively, it had to be a beta decay. But notice how the boron 12 turns into carbon 12 with an asterisk on it. That asterisk means that that carbon nucleus is in an excited state. And when the gamma particle gets emitted, it's a pure photon, mass of 0, charge of 0. We haven't changed the mass number or the atomic number at all. We've just reorganized the mass energy configuration of the nucleus, and mass gets turned into energy, essentially. Binding energy shifts around. And what dumps out is a photon, a packet of energy with no mass. It's not a particle. It is a photon. It's a light ray. It's the most energetic light that we know of in the electromagnetic spectrum. So a gamma doesn't change anything. It just stabilizes the nucleus by getting some of the binding energy to rearrange and get out. Get out. The symbol for a gamma particle, by the way, just in case you want to notice that it's like a fish swimming down, and then those look like bubbles, but they're not supposed to be bubbles. It's supposed to be 0, 0, with the lowercase gamma. Is what that symbol is. Okay, so that was what you were supposed to learn before I taught you about half-life and showed you the radioactive samples. natural sources and decay series. I've got something that looks kind of scary on the screen, but you don't have to memorize this chart or anything. I just want to point something out, right? All elements that are heavier than lead, and basically when we say heavier than lead, if they're not lead 207, okay, they are going to be naturally radioactive. They're going to be naturally unstable. That nucleus is so big, the strong force just simply can't keep it together. And so it's going to undergo alpha, beta, or gamma decays in an attempt to become stable. Again, governed by random statistical processes, but the nucleus will undergo. And so this one is thorium, 220, was it 97? 232, but I can't read, okay? So thorium's right here, okay? So thorium is a naturally occurring, unstable element. I know it's unstable because it's heavier than lead 207. Thorium 232, atomic number 90. So if we look at the decay series, we can see that thorium will go through a series of decays. It does an alpha, and then it does two betas, and then does a whole bunch of alphas, and then does a beta, and then it can kind of split. But notice it's always going to end at lead. Everything, every natural decay series, uranium, palladium, thorium, actinium, okay, all of them come down to lead. That's why lead is kind of this magical last stable thing on the periodic table. There's generally three of these. There's the uranium series, the thorium series, and the actinide series. But of course, bismuth is radioactive too. It's at the end of the chain, so we really don't worry about it. Okay, so I just again wanted to, if you ever hear about decay series, it's putting together the right alpha and beta decays for anything bigger than lead to get down to lead. Below lead, like I said, it's possible but not feasible or practical to cause elements to undergo nuclear instability. Basically what you have to do is you have to kind of throw a whole bunch of neutrons at them and then try to get them to fall apart in the right way. And it's very, very difficult. All right, so now we're going to talk about how we measure alpha, beta, and gamma and quantify it and the unit systems that are in play. I'm going to guess that this is going to be higher on the confusion factor because it always is. When people see this, even for the 10th time after you explain it to them, it can seem very strange and weird, and it seems like there's a lot of units being thrown around. And because it's not used often by the general public, there's a lot of misunderstanding and a lot of heebie-jeebies when people start talking about radiation, and because you don't know what it means for something to be very radioactive, versus not very radioactive. And I'll give you some examples of this. Let's jump into this and see. We're going to come out the other side okay. I'm going to do some examples, and hopefully it'll be a little bit clearer, and you'll have a template to follow. Part of the problem with radiation and measuring it is we are talking about three very distinct things. And we divide those three things into a measure of activity, a measure of absorbed energy, also called a dose, and then what does that dose do to the human physiology, otherwise known as the dose equivalent. So there's three levels there, right? Activity simply measures the presence of an alpha, beta, or gamma event. A nucleus has emitted one of those three radioactive particles, and all activity does is say, yes, that happened. It counts the number of emissions per time. Okay? And I misspoke yesterday. I had forgotten this. And I have an excuse that I'll tell you about in a second. The becquerel is the established accepted SI unit for radiation. The curie is in the imperial system of units. And the reason I can be slightly forgiven for conflating the two is that the SI system has actually been borrowing it and using it in a lot of its paperwork. Like the European nuclear scientists will measure things in curies instead of becquerels. Okay, so the actual usage of these units gets a little bit sloppy too. Okay. So if we're measuring a rate, a number of decays per time, right? The becquerel is a decay per second, and the curie, I did go look this up and I wrote it down somewhere. Maybe. Yeah, a curie is 3.7 times 10 to the 10 decays per second. So a becquerel is 1 decay per second, and a curie is 3.7 times 10 to the 10 becquerels. So if you ever have to go back and forth between curies and becquerels, it's just a lot of the times you'll see International Atomic Energy Agency referencing things in curies because becquerel is such a small thing. Anyway, so that's activity. We're not worried about energy, just did something happen, how many of them happened per time. Absorbed dose is a measure of how much energy per mass was delivered by the radiation exposure. So something has had radiation directed at it, something has experienced the energy coming off of a radioactive substance, and the question here is, how much energy was given to that mass? It's not a measure of energy directly, it's a measure of energy per mass. A gray, the symbol GY is the symbol gray, G-R-E-Y, or A-Y, depending on which side of the Atlantic you happen to be on, okay, is equivalent to a joule per kilogram. So 10 grays would be 10 joules per kilogram, okay? So, or 1 joule absorbed by a tenth of by 100 grams, right? Like it scales. So, notice we're not talking exactly about the energy. If I wanted to know the total energy, I'd have to know the mass that received that absorbed dose, right? To be able to do it. In the United States, and for a long time, until basically the 1990s, the unit, the internationally accepted unit for absorbed dose was the RAD, the radiologically achieved dose, or radiation absorbed dose, there we go, okay? Because the United States was at the forefront of nuclear research with the Manhattan Project and understanding nuclear physics and nuclear chemistry, the units in the United States kind of stuck, right, for a long time. But the RAD and the REM, since the 1990s, the international community has kind of been flexing its muscle and using grays and this other one called a sievert a lot more often. Okay, and unless I'm reading something out of the United States, if I'm reading something internationally, it's always going to be in grays and sieverts. News publications have picked up on this. Only in the United States will you see, if news is covering some radiation event in the US, it's probably going to be RADs and REMs because that's what the scientists said at the press conference. Everywhere else internationally, it's going to be sieverts and grays. The good news is that there is only a factor of 100 between the two systems, right? So it's actually pretty easy to kind of go back and forth, right? If I have a 250 rad absorbed dose, right, then I know that's 0.25 grays. Like you just divide by 100 and you're done, okay? Or 2.5, all right, 2.5. Apparently it's not easy to divide by 100. I'm always used to dividing by 1,000, right? Kilo, right? So I always move it too far and then I have to correct. So that's the good news. But the rad is the same idea as the gray. We're just arguing about sort of where to put the decimal point. And then there is absorbed dose. Or sorry, dose equivalent. See, it even gets confused in my mind. What the dose equivalent is attempting to do is factor what organs in the human body got the dosage? So, if I have an absorbed dose of radiation in my hand, that is way less dangerous than if I have that same absorbed dose in my center body. Okay? Why? What's here? All the vital organs, right? What's up here? The vitalist organ. They all need to work together, right? But like it's really bad to get radiation exposure near your vital organs. And so what the dose equivalent attempts to do is to factor not just the biology, but also the kind of radiation it was, right? So activity and absorbed dose is like, it's just it doesn't care if it's alpha, beta, or gamma. How many of them were there per second? How much energy per mass was delivered? Okay? Dose equivalent, we introduce a new factor that allows us to quantify how bad alpha, beta, and gamma are compared to each other. And depending on the situation, it will also quantify the biological effects of where the radiation hit on the human body. REM stands for radiological equivalent in man, right, in the human body, right? Sievert is the last name of somebody that pioneered, had to honor, I have no idea what they did, don't care, okay? Old white guy, whatever, right? It's the one that's really used most often nowadays. Like, even in some publications in the United States, I'm seeing Sieverts more often than REM. The thing about, so there is it my next, it might be my next slide. 1 second, let me check. Yes, okay, good. I put it together in a slide, okay? Because it can be kind of hard to keep track of what's going on here, okay? The RBE factor, okay? This radiological biological or radiation biological equivalent, something like that. A lot of big fancy words being thrown around here, okay? This is sometimes also referred to as the Q factor, not for heat and thermodynamics, but just like it's a multiplier that's trying to indicate the, not so much the severity, but actually kind of the safety of these things. Notice that gamma rays and X-rays have a Q factor, RBE, of 1. And these are averages. It changes depending on the situation. For example, if you are getting a CAT scan, okay, which is a series of X-rays that are taken, and that CAT scan is of your hand, the Q factor will be very different than if it's a CAT scan of your head. Okay? Again, because of your head, the brain being inside there, right, versus your hand just having bones and ligaments. Weirdly, the safer, the least damaging the radiation, the higher the Q factor. So what's going on here? The dose equivalent, right, the thing in sieverts is equal to the absorbed dose times this factor. So if I want to know the absorbed dose, I have to take my dose equivalent and divide by my RBE or Q factor. Remember, what does absorbed dose tell us? What's absorbed dose focusing on? Energy, right? We need to know how much energy, because once we know energy, I can tell you how bad your future is going to be, okay? Energy is what we really need to know. What the dose equivalent is trying to capture is sort of that energy. But notice, my absorbed dose goes down, the amount of energy goes down, the higher the Q factor, right? So for alpha with an average Q factor of 20, right? If I have a big dose equivalent, like 100 sieverts, I'm dividing by 20 to get to 5 for alpha particles, right? Whereas if it were gamma rays, it would be 200 divided by 1. And I'm getting a lot more energy from a gamma ray than I am from an alpha particle. And to me, this feels a little bit backwards in my brain. It's often hard for me to remember this, right? I always feel like gamma should be a bigger factor, right? It's more energetic, it's dangerous, right? It's gonna get me no matter what. But the opposite is true when it comes to these RBE or Q factors. The higher in the Q factor, the less energy is delivered. Okay? So let me do an example, okay, where we are working with these unit systems and trying to sort of figure out what's going on with a given exposure to radiation. Okay? So we know a certain mass of tissue, human tissue, okay, receives that dose equivalent of a particular kind of radiation, in this case gamma radiation. My detector yesterday, my radiation meter, was measuring in sieverts, right? So it was actively, as it detected the particles coming in, it could distinguish between alpha, beta, and gamma. And in so doing was normalizing, right? Trying to give an indication of exposure that was tied to that radiation type. Now, the thing that meter could not do is determine whether that's coming like to my chest and head versus my hand, right? It can only read through that window. So it's measuring in sieverts, and so we're not getting so much of a kind of a biological thing as we are getting an indication, a normalization, a equal and fair comparison between all the different kinds of radiation that detector was being given. In other words, if it was a lot of alpha, then that could have been equivalent to a little bit of gamma, right? And the detector is actively figuring out what those particles are. Again, positive, negative for beta, and then no charge for the gamma. You can figure that out. And then it knows what kind it was, knows the energy that it had as it came into the detector, does the calculation, gives it out in sievert. It's the most common. You don't run around with a detector that's measuring in rays. Okay? You're almost always using a detector that's measuring in sieverts, and that detector is constantly checking what kind of radiation it is and giving you this normalized number. Anyway, so we know that our dose equivalent in sievert, and you just look at the unit, right? Even if you're getting confused about like what's a dose equivalent, what's an absorbed dose, that word dose gets thrown around a lot, doesn't it? Right? Just look at the unit. Sieverts is all about that number, that Q factor that is trying to keep track of the kind of radiation involved, right? And in this problem, we want REMS and energy, okay? REMS and sieverts are measuring the same thing. They're all about that Q factor, that RBE factor. And I know, based on my, the previous slides, okay, that it was, oops, not that slide. Giving stuff away. I know that there were, what was it? It was, there was 100 sieverts in one REM, is that right? The other way around? I'm glad I have you guys around. Keep me in line. Okay? A factor of 100 different, right? Okay? So, since I know 0.8 times, well, okay, I'll stay in millisieverts, okay? And I know that there are 0.01 sieverts in one REM. The milli is going to carry over. And what's 0.8 divided by 0.0? That's 80. 800, but then there's another point in there. So that's 80. And then this would be millirem. You can change milli times 10 to the 3, right? And keep that times 10 to the 3 floating through there. It all ends up being the same. So that's the answer to part A, right there. Okay, find the dose in REM. And that's the factor of 100 difference, okay, between the two scales. All right, now they want to know how much energy was absorbed. So what is the unit of energy that we are after? It's SI unit of energy. Joules. Okay. So what do we need here? In order to figure out energy, which of the three things? Is it activity? Is it dose equivalent, or is it absorbed dose? It's absorbed dose, right? Absorbed dose is grays, and a gray is a joule per kilogram, right? 1 gray is 1 joule per kilogram. So we have to find out how many grays we've had here. So how do we get from dose equivalent to absorbed dose? The dose equivalent is equal to the absorbed dose times the RBE or Q factor. Did I get that right? Last slide, okay. So, what is the Q factor for gamma? Do you remember? It's 1, right? It's always the one I can remember, right? Gamma's 1. Okay? So that means that if my absorbed dose is 0.8 millisieverts, and I multiply by 1, I'm going to get 0.8 milligrays. Multiplying by 1 was never so easy, right? Okay, so that's my absorbed dose. Shoot me now. Just shoot me now. Apparently multiplying by 1 isn't easy. I want my absorbed dose. It's dividing by 1. There you go. Multiplying by 1 over 1 equals absorbed dose. So it would be 0.8 millisieverts divided by 1 to get me the 0.8 milligrays. There we go. See? This is what happens when you don't do it for a whole year. You guys are brand new, so you're allowed to make mistakes until you get to the exam, and then I'll. All right, so now how do we find out how much energy this was? This is a energy per mass, isn't it, the gray? A joule per kilogram. So how do we figure out the total number of joules? We multiply by the mass, don't we? This is equal to 0.8 millijoules per kilogram, right? And if we want to get, so let's see, I know that I have 0.5 kilograms. And if I do that, the kilograms cancel. And I'm left with joules, right? Well, what's half of 0.8? That's 0.04 millijoules. I'm just carrying the milli through. It's a factor of 1,000, it's just kind of along for the ride. So there we go. There is the amount of energy that was absorbed by that tissue, okay? If there had been more mass, right? If it had been 1 kilogram instead of half a kilogram, right? The amount of energy would have been lower, right? Because remember, the gray is a joule per kilogram. The more mass you get, the less total energy gets absorbed. Okay, now repeat the calculation, but with alpha particles. Okay, so does the amount of energy change based on whether or not it's a gamma or an alpha particle? Yes, right? Because the dose equivalent in sieverts, right, depends on this Q factor. So if I take this down over here, right, my dose equivalent is still 0.8 millisieverts, but my Q factor for alpha is 20. So now I'm dividing by 20, not 1. And now I'm getting 0.04 milligrays, 0.04 millijoules per kilogram, and then I use that 0.04 millijoules per kilogram or milligrays, and I multiply by my 0.5 kilograms of mass. It gets me 0.02 millijoules. Well, surprise, surprise, if you take, I made a 0 mistake. No, I didn't.
Eligible for the first one. I think it's just 0.4.
0.4, that was my 0 mistake. I got excited about dividing by hundreds. This is 0.4. Yes, it's 0.8 by a half. No extra zeros in there. The difference between 0.4 millijoules and 0.02 millijoules, surprise, surprise, is a factor of 20. See how so there's 20 times less energy that got absorbed because it was alpha particles versus gamma particles. That's what this dose equivalent is attempting to do. It's attempting to make sure that we are putting like alpha, beta, and gamma on equal footing in terms of their potential to do harm to human bodies. Okay? The Q factor, like I said, changes depending, I gave you averages, right? But it changes depending on the type of radiation and what is being exposed. So you'll end up with Q factors or RBE factors for certain scans of different parts of the body being much higher or lower depending on the relative biological effectiveness. But let me give you an idea. I'm trying to calibrate you, okay, so that you understand. Some of you are going into medical school or medical professions, whether it's physical therapy or PA or doctor or whatever, right? You are going to be likely in or near facilities that have radioactive sources in them. You might be working in a hospital. You might be working in private practice where they're doing radiation therapy as part of the physical therapy. Even though physical therapists don't get trained in it, sometimes the practice has the radiation thing on the other, just one side of the wall, right? And because you're in that building, you might be asked to wear a radiation detector, a device. Nowadays, they're almost always in, like if you're given a key fob or an ID card, so like a nurse or a doctor's ID that specifies whether it has the radiation dose counter right built into the card, okay? And it can be read, I think nowadays by NFC, but they used to be able to be turned in your card and they would give you a new one to measure the dosage. Anyway, so just want you to be vaguely aware of like, what constitutes normal? What constitutes dangerous, right? In all of these things. So I've given it both, in case maybe you end up in a place that still uses REM, but most often it's going to be sieverts, and again, just a factor of 100, okay? But the annual exposure that the general public, somebody who is not working in a field related to radiation, will receive is about 0.0013 sieverts. 1.3 millisieverts, okay? So basically, I always remember this as like 1 to 1.5 millisieverts, right? My detector yesterday was measuring in microsieverts per hour, right? So at an exposure of 10 to the minus 6, right? 10 microsieverts per hour. I'd have to wait an hour for one of those NRC exempt nucleotides to give me 10 microsieverts, right? And then I would have to wait for 1,000 hours for that to even be a millisievert. So a factor of 1,000 there matters on that scale, right? Because it takes a much longer, it's such a small amount of radiation. So the average annual exposure to the general public, which I guess technically I am not a member of the general public because I do maintain a repository of radioactive materials in the back, is going to be roughly 1 to 1.5 millisieverts. However, in US law, nobody can be exposed to more than 5 millisieverts on average in a given year at their workplace. Okay? So if you're running a X-ray machine, okay, if you're running a particle accelerator that's making radioactive isotopes for the contrast for the X-ray machine, if you are helping cancer patients with radiotherapy, whatever, right? Okay, there is an upper limit to the amount of radiation that OSHA says that you are allowed to be exposed to, and it's 5 millisieverts. Pilots, stewards and stewardesses, anybody that operates at high altitude also is limited by this. The number of hours that a pilot can fly in an airplane, there's 2 measures. Pilots in the United States cannot fly for longer than 12 hours at a time. In other words, from the time they start flying the airplane to the time they stop flying the airplane has to be less than 12 hours. Some airlines don't even do that, they do 10. Okay? That's a safety thing. It's a awareness and being awake and not being tired, right? Type of thing. But there's another measure that is the total number of hours in a year. And if a pilot is approaching their maximum flight time for the year, they have to be grounded. And the reason they have to be grounded has nothing to do with their safety and ability as a pilot. It has to do with the amount of radiation they've been exposed to. Why are pilots being exposed to a lot of radiation? They're high up in the atmosphere. They're closer to the sun, right? And they don't have the protective blanket we have, right, down here at sea level. So that includes the flight crew, right? All the stewards, stewardesses, anybody that's serving the passengers, right? Even passengers technically, but if you're a passenger doing that much time in an airplane, I feel for you. Like if that's not your workplace, wow. Okay, so it better be your workplace if you're doing it. So notice, right? We have to get from 5 millisieverts up to 250 millisieverts before we even see the slightest effect on your biology, right? I think that's a factor of 50, okay, between those two numbers. It's like the amount we are legally allowed to be exposed to versus when we actually get radiation sickness is huge. At 1,000 millisieverts, okay, radiation sickness becomes evident. That's when you as a person go, I don't feel good. And a doctor can look at you and go, I've never seen that before. Okay? Or hopefully, right? But that's where you start. Radiation sickness is categorized as nausea, vomiting, diarrhea, lesions. If you're getting lesions on the skin, you're way beyond radiation sickness. General discomfort. Your organs are starting to, they're not failing, they're misfiring. Okay? Your stomach goes a little haywire. Your body is acting as though it's been poisoned. Right? Your body doesn't know what's wrong, and so it says, oh, poisoning, and you start throwing up. Okay? And we talked kind of about with motion sickness, same sort of response from the body. At 2 sieverts or 2,000 millisieverts, you are starting to damage the bone marrow. You have a increased chance of getting leukemia, which is cancer of the blood. At 5 sieverts, if I walked back there and grabbed a 5 sievert source and I just exposed everybody to 5 sieverts in this room, statistically, 50% of us would die as a direct result of that exposure. I want to be very careful here. I'm not saying you're going to die. Like, drop off instantly. Go get sorted. Boom, half dead. No. It takes time. It's miserable, okay? But 50% of a population, if exposed to that, are going to die as a direct result of the radiation exposure. At 10, you're done, right? Is everybody goodbye? That is definite death. It will happen. It's simply a question of how long. So, and that gets dark at the end, doesn't it? Right? But notice how big a difference there is compared to what's normal, what's legal, and then even getting the first inklings that anything is wrong. Some of these numbers are a little bit outdated. I need to update this slide. But there are lots of sources of radiation, natural and artificial. I've scaled some of these things here for you. It's easier to see maybe in a pie chart, okay? But notice, most of your radiation exposure comes from nature. Nature is radioactive, okay? And, the diagnostic stuff we use in modern medicine today does expose you to ionizing radiation. X-rays are included in that. They can ionize and therefore cause problems in DNA replication, which leads to cancer and some of that kind of stuff. But unless you are getting an X-ray a day, don't do that. An X-ray a day definitely brings the doctor on, okay? There is a maximum amount you're technically allowed to be exposed to, but most modern medical systems in the United States have a lot of difficulty keeping track. Unless you're in a system that is highly integrated in keeping track of your medical history, a doctor doesn't necessarily know you've gotten 5 X-rays from that doctor and they order 10 or something, right? Okay, so keep an eye on it as you get older. Right? Make sure you're not being exposed to too much, right? And then consumer products do give off some. And notice television sets is listed on this slide. That's the old CRT monitor type, the big fat ones, not the flat screens. Flat screens are different, okay? The danger with flat screens is the content you are watching, not the actual physics of the device. In the old CRTs, it was both content and the fact that an old television shoots a beam of electrons at the screen very fast. What's a beta particle? It's a very fast electron, isn't it? Notice, it didn't say your TV makes beta particles. It doesn't. You're just being exposed to some very fast electrons which can ionize. Most of their energy gets dissipated in the phosphor, but some of them go through. This is why your mother said, don't get too close to the television. No, your mother had no idea about it. She was worried about your eyesight. Okay, let me leave you in the last 5 minutes. This chart was made by the genius that writes XKCD, which is a web comic, okay, that has a very science bend to it. The gentleman that runs XKCD was sick and tired of people misunderstanding radiation, okay? And so he came up with this chart. I know it's very difficult to see this chart. The writing's too small, all that kind of stuff. I want you to see the whole chart because I'm going to zoom in on portions of this chart, okay? So we're going to start with the blue part, but notice everything in the blue gets squeezed down to this green area, and this whole green area is going to get squeezed down. And so basically we're going to increase radiation dosage as we go through this chart. But let's zoom in on the blue side. And again, I know it's a little bit small, so let me guide you through this, okay? So 2 blue squares, visualization of what's going on here. 2 blue squares is the amount of radiation you get from eating a banana. Potassium 40 in bananas, right? Potassium good for your muscles, right? And making them function and not get cramps, right? Okay? Eat bananas. Don't stop eating bananas because bananas are great, okay? By the way, in the 1970s, physicists did try to adopt the unit of bananas for radiation because people weren't understanding rams and rats and seabirds and grapes. I just don't understand. And so if you said the radioactivity of 1,000 bananas, people would have some way to connect it. The banana lobby went completely ape. Like went to Congress and said you can't let scientists do this, and in fact that's exactly what happened. Banana is not allowed to be a unit, and we still use it internally in physics though. We'll talk about how many bananas somebody got exposed to. Okay, so There's a banana, 2 blue squares, okay? Half of a banana, 1 blue square is if you sleep next to someone for a year. That's half of a banana, okay? Living within 50 miles of a nuclear power plant gives you 3/4 of a banana. Okay? 6 of these squares if you live within 50 miles of a coal power plant. Wait. Why are coal power plants more radioactive than nuclear plants? Where does coal come from? The ground. The ground is radioactive. Guess what's not controlled when it comes to the emission of coal power plants? Lots of stuff is controlled. Pollutants, carbon dioxide now, blah, 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 right? What's the one thing that is not measured or controlled from a coal power plant? Radiation. You're burning coal and sending those products up the stack. The radioactive stuff comes out and is not captured. Coal power plants are 4 times more radioactive than nuclear power plants. Here's an X-ray in your arm. This is living in Colorado. Why are people in Colorado exposed to more radiation?
Higher altitude.
Eat more bananas. Higher altitude, right? Higher altitude right there. Here's your dental X-ray, okay? This is the excess average dose following the Fukushima nuclear disaster in Japan, okay? Here's your background dose from a normal day. Being inside, outside, walking around, yada, 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 right? A lot of bananas, okay? And here's an airplane flight that takes you from New York to Los Angeles. How bad was Fukushima? And yet people freaked out. How many bananas? How many sieverts? 0.01 more microsieverts per hour? Ah! It's nothing. I remember the news article when Fukushima happened. And it was awful. The tsunami, the earthquake, the subsequent release of radiation, they were bad. The loss of life, all of that. We're going to talk about it later. There was an article about how scientists measuring milk from cows in Tulare detected the presence of radiation, elevated radiation levels in the milk. Every power plant has a fingerprint. We know exactly where the radiation comes from because every power plant has a slightly different mixture of blah, 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 blah. Okay? We knew it came from Fukushima. Okay? The article was alarmist and people stopped buying milk from California. The amount of elevated radiation as indicated in the article was an increase of 1 picosievert. And people went, unintended, bananas. Right? A picosievert we can measure? Does it matter? Got milk? We will continue with this on Thursday. There's going to be some rants. I warn you right now. If you have your quizzes, you can go ahead and throw them up here on a pile.